I am HS Negi from Snow and Avalanche Study Establishment SASE from Chandigarh. So the outline of this presentation is, first of all I will be talking a brief about snow and reflectance, then hyperspectral remote sensing, then spectral properties of snow, then field investigation using a spectroradiometer for Himalayan snow, then selection of suitable wavelength for snow cover characteristic, and then snow cover monitoring or snow characteristic, that's like snow grain size, albedo, snow mixed object. I will be discussing on this, and finally the outlook. So first of all, to understand the object, that is the snow. So what is snow? Snow is a porous permeable aggregate of ice grains, and once snow is at very low temperature, this will be a two-phase material, that is ice and air. So there will be the matrix of ice grain and air in between. So once the snow is close to 0 degree centigrade, it becomes a three-phase material where the moisture appears in the snow. So the snow forms in the atmosphere in the presence of the water vapor, and once the temperature is at sub-zero, and first of all this nucleation take place, and ice crystals forms. So once the ice crystals forms, then again by the sublimation growth, this snow crystals are formed, or from again by the riming process, the gropels form, and again by the aggregation of these snow crystals, snow flakes are formed. So this is the formation of the snow in the atmosphere. And once the snow falls take place, and on the earth's surface there is the snowpack, so metamorphism start taking place. So metamorphism is basically the change in the shape, snow grain size, and the shape of the snow grains. So this metamorphism can be by two methods, either by the thermal or by the pressure. So there are two types of metamorphism: thermal metamorphism and pressure metamorphism. In thermal, again this thermal is divided into three classes. One is equitemperature metamorphism, and the another is temperature gradient metamorphism, and the third one is melt freeze type of metamorphism. All these metamorphism, I am not going to detail on this, but this is just in the snowpack. If there is that temperature gradient is there, then temperature gradient type of metamorphism take place, and because of all these different metamorphism, different type of snow grain size form. Like in the melt freeze cycle, so in the daytime, if the temperature is very high in the positive side, so melting start taking place, and and again at the night time these snow grains then the freezes. So that is a melt freeze type of snow, that is called melt freeze snow metamorphism. Then it is important to understand first of all what is snow, what is ice. So snow, as I've said, this is a porous material, and after the densification, after this pressure metamorphism, it converts into ice, and you can see the density from this table, that for the fresh snow, very low density is there, 100 to 200 kilogram per meter cube, and for this ice, that is normally 917 kilogram per meter cube. So you can see how this density varies from 100 to 917, and after the 1 year, this snow is start changing into fern, that is called fernification, and again that is its density is in the range of 400 to 800 kilogram per meter cube. So this is just a brief about the snow, and now you will see that snow covers a very large extent on Earth land surface, and it has a very high albedo, and because of that it influences the earth radiation balance. And this albedo is also changes by this changing physical characteristic of snow cover. So once we know the albedo, then by the inversion technique we can estimate the snow cover characteristic. And the snow cover has lot of application in climatology, hydrology, and glacier study, information map for study planning, avalanche forecasting, flood forecasting, and in many other developmental activities which contributes to our national economy. So now coming to hyperspectral remote sensing. So initially this panchromatic data, when we talk panchromatic, that's a single band data and which has a very low spectral resolution. So then comes multispectral. So in multispectral, more than 2 bands up to 10 bands, and which is having then medium spectral resolution, you can say. And but in the hyperspectral, at the same time you have hundreds of bands, more than 100 bands, and the spectral resolution is also very high. So from the panchromatic data, you can do the deduction. That's a you can determine the presence of material, object, activities, or the events. At the same time, from the multispectral data, you have advantage. You can discriminate. You can classify between the different classes, and then apart from these, in hyperspectral, you can also quantify uh, the material. You can determine the abundance, the percentage of the particular material in a particular pixel. Then comes characterization. Here you can, in hyperspectral, you can characterize the material based on like wetness, based on this particle size, like that. And you can also identify, once you know the particular signature, you have some particular signature, you can identify from the satellite imagery the similar spectra all over the image. So these all are the advantage of this hyperspectral remote sensing. So in hyperspectral remote sensing, there is the data is collected into narrow bands, many narrow bands, as well as in the contiguous wavelength bands. And you have the image, and for a particular pixels, if you take one spectra, so you will get the spectra like this, and where you have these absorption band. Clearly you can observe all these, where such absorption feature you cannot find with the multispectral or in the panchromatic data. So here you have the advantage, you know these absorption features and why these absorptions are there. Then based on that you can classify, you can understand that the characteristic of the material. So this part, that spectra part, is come under this hyperspectral spectroscopy, and the another is the imaging, the spectral imaging. So spectral imaging which captures the complete hyperspectral image. So what's the use of these hyperspectral spectroscopy? So as I've said, here in the hyperspectral data you can characterize the object, you can quantify, you can identify various targets. But apart from that, from this hyperspectral spectroscopy you can design your remote sensing sensor based on this maximum minimum radiance reflected from the target. Then you can select the various suitable bands to characterize particular target. Then you can develop various indices based on these selected bands. Then you can do a lot of atmospheric correction using different bands, and you can estimate the albedo. Then you can do this subtle classification of the target, and of course this hyperspectral data is used for this your field validation and your library generation. So I'm coming to first the radiance characteristic of different objects. So you can see how the radiance look like in this complete short wave range, right from 350 nanometer to 2500 nanometer range, and this is for the water, very low radiance. Then comes, this is for vegetation, this is for soil, and this is for the snow. So whatever our satellite sensor measure, that is the radiance characteristic, and you will see that these radiances, this depend also on this intensity. So here you can see the fresh snow uh, radiance at 1030, it is something up to this 25 milliwatt per centimeter square per steradian per micrometer, and at the same time, after once this uh, intensity increases, this radiance also increases, and that's why for our classification we used to convert these radiances first into reflectance, because reflectance is the inherent property of the material, and then you do the classification. So from based on these radiance information, you can see that when you design these sensors, uh, you know what should be the maximum radiance for particular objects. So earlier uh, there was the sensor in the HRS series, like in list 1, list 2, list 3. All these sensors was saturating in case of snow. So because if you see the snow radiance from the top one table, all these radiances are higher than these maximum radiances in the sensor. So all these sensors up to list 3, these were saturating, its bands were saturating in case of snow. So but in case of AVIPS, IRS P6 sensor, that's AVIPS, so here its maximum radiance is higher than whatever we have observed for the snow in the field. So here you can say this sensor saturation is one of the problem in case of snow in the earlier sensor, but now like in AVIPS, this type of sensor saturation problem is not there. Now this is the spectral reflectance signature of different objects. So you can see from the water has very low reflectance, and then in NIR region this is almost 0. Then for this is for the vegetation, then for the soil and the snow. So snow has very high reflectance in the visible region. So I will mainly talking on now this snow reflectance. So this is the typical spectral reflectance curve of snow. So you can see the reflectance is very high in the visible region, and then it descends in the NIR region, and in the sweet region it's almost flat, very less than 10 to 15 degree 15%. So in the NIR region you will find that there are the maxima at 1100, 1300, 1900 and 2200 nanometer range, and these maxima are corresponding to these minima absorptions here, and these minima can be explained by this refractive index of ice. So these minima are corresponding to absorption. There are more absorptions, like here 1.1 micrometer, then 1.3 micrometer, and then in this region where these peaks of more absorptions are there, will find these minima over in this spectral reflectance curve. So this spectral reflectance of snow, this depends on the snow grain size, the contamination, the water content in the snow, then snow depth, and these are the physical properties of snow, and the other properties that depends on the solar zenith angle and the cloud cover. So here it is important to understand this refractive index of ice. So refractive index of ice, which is a complex term where there is a real part as well as the imaginary part. So real part denotes the velocity of, this is a ratio of where the velocity of light to the velocity in the medium. So this comes in case of ice as well as water. You will find the real part is almost similar, flat. For the ice it is around 1.3, and for water 1.33. But this imaginary part, which is also the absorptive part, here you will find this a significant change throughout the wavelength. If you see that this is the order of 10 to power minus 9 to 10 to power minus 2 or 3. So a lot of variation take place in the refractive index of this snow, this ice and water. And you can see that this is almost parallel, and this coincide, this ice and water imaginary part. And here this is the sway region, where this is between 1.5 to 1.7 micrometer range. In this region, here this ice is more absorptive than the water, and this is the region where you can discriminate between the water cloud and ice cloud, as well as this is the region where you can discriminate between the snow and cloud. So in the cloud there are very fine grain size. However, in the snow there is larger grain size, so that so larger grain size absorb more light, so snow appears dark in this region. However, the clouds appear white. So this you can understand with this list 3 image. If I open this list 3 image in green band, so cloud as well as the snow both are appearing white here. But if you open this image in sway region, so you will find that the snow appears dark in this region, and but still cloud appears the white. So here in this sway region, in sway band, one can discriminate between snow and cloud. Secondly, you can also understand these absorption phenomena by the, like, there are different process, electronic process, vibrational process, and this rotational process. So in this NIR region, because of the overtone of these vibrational process, there are the absorptions. So and these absorptions are due to the water molecule H2O, and because of this H2O molecule, there will be these vibrational process where this bending, stretching, and this is that is bending, stretching, that may be symmetric stretching or anti-symmetric. So based on these modes, these vibrational process, these are the absorptions in this NIR regions. So mainly these vibrational process are in the from 2 to 6 micrometer range, but here these are the overtones of vibrational process. And the other process, like electronic process and rotational process, so in micro region there will be the rotational process. However, in this visible region or near UV region, you will find because of the electronic process. So these are the absorptions, why these absorptions are there in this spectral characteristic of snow. Now, how this snow grain size, how the reflectance varies with the snow grain size. So you will see here these are the reflectance of varying grain size. So as the grain size increases, right, from 50 micrometer to 1000 micrometer, so the reflectance decreases in this NIR region as well as in SWI region, but here in the visible, this is least affected by this grain size variation. So with the grain size variation, this effect comes in the NIR region. So later on I will go into detail of this grain size variation. The second is the effect of contamination. So contamination is basically the pollution. That pollution may be through the soot, black carbon, or by any other like by dust. So you will find that once the contamination increases, so in the visible region the reflectance decreases, and this decreases significantly. So these are the experiment carried out by Warren and Viscombe. So this this is the reflectance uh, when they mix the soot by parts per million by weight. So once the soot increases, the reflectance decreases. So you can also find that what they have found. So even the grain, the soot amount is same, but the type of snow is different. Here the the snow grain size it's 100 micron, and however if they taken 1000 micron grain size, so there will be more absorption with the same amount of the soot. The third is how this albedo varies with the liquid water content. So you will see that uh, for this one interesting experiment conducted by long back in 1975 by O'Brien and Moniz. So what they found, they have observed first the dry snow reflectance, which is shown here by this dotted lines, and then uh, they have blown the hot air in the snow pack, and the moisture appears in the snow and its wetness increases, and once it was a wet melting snow, they took the spectra of that and they found this reflectance curve. After that again they have refreezed the sample, and they have again took this reflectance, and they have found the spectral reflectance is again of this refrozen snow is the same. So if there would be any effect of the the wetness, so ideally this reflectance of the snow after refrozen, so because it became dry after that, it should ideally go up as in the previous case, so as it was here, but it remained there. So it shows that here in this NIR region, uh, the effect of wetness is this the decrease in the reflectance is not by the wetness, but this is by the increase in the grain size. So how this increase of the grain size took place? Actually, once the moisture is appears in the snow, so the cohesion within the different snow grains takes place, and the grain size increases after the cohesion, and the effective grain size increases with this cohesion, and the snow grains this reflectance remained low after. So later on, then Green and this Dozier, 1994, they have found that these liquid water, there are the absorptions, and they have found there is slightly shift. We have collected various spectral reflectance of different type of snow and ice and other ambient object. So we are having this ESD spectroradiometer, and which was in the complete wavelength range from 350 to 2500 nanometer range, and uh, at the time of this field experiment, we have collected various other information like snow grain size, uh, its albedo through pyranometer, that is broadband albedo. I'll be talking on that part also. Then the density of snow, moisture content thermometer. So I want to say that all these the ancillary information should be collected whenever you perform this collection of signatures. So and then we try to develop this spectral library of the different type of snow. There's a fresh snow, old snow, uh, with varying grain size, moisture, contamination, like that. So this is the grain size variation. You can see again the experiment conducted by us, how the reflectance decreases in the NIR region with the increase of snow grain size. So here uh, what we have found from this type of experiment, we have estimated what is the most sensitive band where there is the maximum variation in the grain size, and then we have found the wavelength region 1050 nanometer, that is 1.05 micrometer range. This is the wavelength where which is most sensitive for the snow grain size. Secondly, what we have observed here in this Swir region, so in Swir region, that is again from 1600 onwards, so this is more sensitive for the first from fresh snow, very uh, uh, the fresh snow, like which converted like from the dendrite to medium snow grain size. So and after that this also becomes almost flat in the Swin region. uh, then it's about this estimation that I'll be talking later on. Then this is the experiment which was conducted for the varying moisture content. So again, due to the moisture, as I've said, very small variation in the reflectance, but as the increase in this moisture content, you'll find in the absorption there is slight shift that was observed. So once you have the hyperspectral type of data, you can find these small changes in the absorption bands. Then for the contamination study, what we did, we have uh, done an experiment by spraying uh, the black carbon or soil and the different S in a fixed field of view under this the sensor of spectrodiometer, and estimated the reflectance. So you can see with the as this contamination uh, increases, as I've said, there is a change, decrease in the visible bands. But here, what we have found, this variation is there in the even in the NIR region and in the Swir region also. Secondly, uh, based on the type of contamination, there is the decrease. So like even for the coal, at the same amount of 1 milligram per square centimeter, there's lot of the decrease in this reflectance. However, there is slight decrease in this in case of soil. So this black carbon of uh, type of contaminants, that can a small amount of the contamination from black carbon contaminants, that can melt a lot of the snow. So then again, we have carried out uh, the 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 soot concentration estimation using the reflectance. This is the basically the aim. Can we estimate this soot concentration? So for that, we have mixed the pollution, the soot in a uh, in a known volume, and collected these spectra. And these experiments were conducted in very in the cold chambers, very low temperatures, and from that we have uh, tried to make empirical relation from where, if you know the change this absorption coefficient, then you can estimate the soot concentration. So there we have found a very good correlation between the actual the concentration and the observed concentration of the soot. The another type of problem you see in the snow cover. So one is the contamination that is studied, and the another is the patchy snow. So at the late winter, the snow remains in the patches due to these the ruggedness in the mountain topography. And to monitor such snow cover, again we have conducted experiment in a fixed field of view with different proportion of snow and soil. We have measured the reflectance, and we have found that this reflectance decreases as this proportion of soil increases in the visible, and the inverse relation has been observed in the sway region. So there the the reflectance increases with the increase of this soil proportion. However, in case of contamination, so there was the continuous decrease even in this sway region. So here you can, even with the hyperspectral data, if you are having the hyperspectral, you can differentiate between the contaminated snow as well as with your patchy snow. The another experiment we have conducted for the snow depth. So to find the effect uh, of the snow depth on the snow reflectance, and for that we conducted the experiment by taking a black sheet and inserting that black sheet in the snow pack, and by observing the and observe the reflectance. Again we took out this black sheet, inserted, and like that we have conducted this experiment, and we have found that for once the snow thickness is less than around 5 centimeter, this effect has come over there. So you can see in the visible region that the one's thickness is less than 5 centimeter, then there will be the effect of uh, the thickness in the snow reflectance. Then we have also conducted the experiment for various slope and aspect, and by making arrangement where this we can tilt this platform and put it in also in different aspects, and then from this experiment we have found that these are the spectra for the north, east, south and west directions, and this is with the different degree slope. So what we have found that there is one indexes that is called normalized difference snow index, and I'll be talking later on this normalized difference snow index. So what we have found, if this slope, this NDSI basically take care of these topography effects. Well, even there is the slope, but this NDSI will remain same. The another problem in the snow cover monitoring is the mixing of vegetation. So, or to measure the snow under vegetation, and for that again we have conducted the experiment by putting the different proportion of vegetation and snow, and taking the spectra, and what we have found, this is for the pure snow and this for the pure vegetation. So once this proportion of vegetation is increases, the reflectance decreases here, but a, a finding here that this red edge here, this peak is coming once there is the mixing of vegetation. So you can estimate the proportion of different vegetation with the help of the hyperspectral data. Then this is for the snow and soil proportion. This I have discussed earlier. So we have tried to find out the suitable wavelengths for snow characteristic, and we have found for the grain size, 1040 to 1050 nanometer, this the wavelength which is most sensitive. Then for the contamination, it's a 470 nanometer. For the snow depth, 590 nanometer is the most suitable wavelength. Then for the moisture, this is 980 and 1160 nanometer. So there are these wavelengths, or 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 the presently operating the optical sensors which do not saturate for snow. These we have discussed here, but if we see the hyperspectral instruments, in hyperspectral imaging, we'll find that there is most of these sensors are airborne sensors, and there is hardly the sensors, the spaceborne one is the, here you can see the Hyperion, so EU1 on board on UN satellite, this one, and this high C from the India. So these are the spaceborne, only spaceborne sensor right now. When we talk about snow cover monitoring, so two things are there. One is mapping, so mapping of aerial extent of snow, and the another is snow cover characteristics. So mapping can be done by various methods. So that, like from the visible band reflectance, from by the different classification technique, by the snow indexes that I will be talking. Then by the now the advances there is the sub-pixel classification, that the avoidances you can find with the, that is the added advantage from the hyperspectra, that hyperspectral data, that you can do the sub-pixel classification. Then coming to the snow cover characteristic, there is, you can estimate the albedo, snow grain size, contamination, moisture in the optical lesion, and these are the property which can be estimated. This is snow surface temperature from thermal, and this snow water equivalent, and snow depth from the microwave has the potential over there, that it can measure the snow depth and snow water equivalent. So like there is NDVI, normalized difference vegetation index. Similarly, in the case of snow, we have normalized different snow index, and this snow index is generated again based on the reflectance curve. In the green, we have observed maximum reflectance. In the sphere region, there is the minimum reflectance of the snow, and based on these two bands, this normalized difference snow index has been generated. And this NDSI, if you see in case of snow, that this is the index which can be used for the mapping of snow pixels, snow, and normally there is a threshold value of 0.4 for the mapping of snow cover. So once this value is more than 0.4, between up to 1, so there, that is will be a snow class. But there the limitation is that the water pixels also merge in this range, so one has to mask these water bodies first, and then can be applied for snow cover mapping. So we also do this snow cover mapping for complete northwest Himalaya, and this is again based on the NDSI, and we have made the criteria NDSI greater than 0.4, and this reflectance in band 2, that's the NIR band, that should be greater than 11% in case of snow, because otherwise the other this water, to discriminate that water body from the snow pixels, and this algorithm also take care of snow under vegetation. So, and finally we generated this type of snow cover maps, and this is the aerial extent of different winters in the Himalaya, and this type of aerial extent plot or the depletion curves are very useful in the snow melt runoff modeling. There is one more index that we have developed, that's for the snow grain size, and based on again the wavelength region 1040 to 1050 nanometer, and where the this band is more sensitive for the grain size, and least sensitive band is 590 nanometer. Based on that, this grain index has been generated for using the hyperspectral data. But for the operational purpose, right now, since we are not having any operational hyperspectral sensor, so we have from this MODIS, where we have the band 4, this close, that's a green band, and this band 5, that's a uh, that's a 1240 nanometer. So with these two wavelength, we have generated this grain index using MODIS, and this grain size map has been generated. So, and this we also validated with our ground observed snow meteorological data. So now I am coming to the another application, that's snow albedo. So first of all, what is this reflectance? So reflectance is defined by this pi L by divided by mu 0 ED. So here L is the radiance and ED is the direct irradiance. So this reflectance is basically the fraction of incident light which is reflected from a surface. So here this solar geometry and the viewing geometry, these angles are very very important, and this mu is called the cosine of the viewing angle, and mu 0 is the cosine of solar zenith angle. Similarly, this phi 0, these are for the azimuth. For phi 0 is for this solar azimuth angle, and phi 1 is for the viewing azimuth angle. So these angles are very very important for the reflectance measurement. Then the another is there is the plane albedo, that we also call directional hemispherical albedo or the black sky albedo, where we consider this direct radiance irradiance, and this is the integration of, basically this plane albedo is the integration of the reflectance for all viewing angles. So all viewing angles, sensor viewing angles, that will vary from 0 to 90 degrees. So this is 0 to 1, and this spherical albedo, or that also called bihemispherical albedo or white sky albedo. So white sky albedo is all because of here the irradiance is the diffuse irradiance is there. So this is the integration of this reflectance for all viewing angle as well as for all solar angles. So there is the triple integration over there. So this is called the spherical albedo. Then comes the broadband albedo, that we normally measure using the pyranometers, the two pyranometers up and down, and there we use this plane albedo, and F is the downwelling irradiance. So once you have downwelling irradiance, you have this plane albedo, one can estimate this broadband albedo. So broadband albedo, this is the integration for all short wave range, right from 350 to 2500 nanometer range. So complete short wave range you integrate for all the wavelengths. So that is called broadband albedo. So what is the need of these spectral albedo products? Like earlier I was talking plane albedo or the spherical albedo. So this Warner, they describe the theory and algorithm to retrieve global maps of land surface albedo for MODIS and MSI using MODIS and MSI data, and its operational products were available as MOD 43. But all these products, whatever these product they have given, this is at the 16 days average product, because it has to consider all the geometry of different viewing angles, solar zenith angles and all, and based on that they developed these spectral albedo products. But if in case of our Himalaya, there is a lot of variation in the seasonal snow cover. We can't uh, uh, we can the albedo changes here very fast. So for that, because of different altitude, slopes, and snow metamorphism in our area, this proceed very fast. So this Kokonavsky and Sierra in 1994, they have retrieved this spectral albedo using AATSR. This is a sensor on board on NVSat satellite, using asymptotic radiative transfer theory, that is ART theory. And here I will be discussing on this theory. So I'll be giving this brief background about this radiative transfer theory for snow. So radiative transfer theory, this describes basically the interaction of light with any turbid media and the solution of radiative transfer equation used for the internal properties of the material. So this is the radiative transfer equation, and where the the important optical parameters are mu, that's a single scattering albedo, the the tau, this optical thickness, which depends on this extinction coefficient, and the third is p, that's phase function. So these three are the important optical parameters. Single scattering albedo is called the ratio of scattering cross section to extinction cross section, and extinction is the this is the scattering as well as the absorption. Then the phase function, this describes the angular distribution of light is scattered by a body when illuminated from a specific direction. And this asymmetry parameters is also there. There's the mean of the cosine of scattering angle. So the solution of this radiative transfer theory is, this is a very complex task, and for this different models has come for the snow using this radiative transfer theory. So first attempt was done by this Dunkel and Wavin in long back in 1956, and they have used this two-stream approximation theory, and which is based on the diffusion model. So after that, this Boran and Barkstorm, and then Warren and Viscombe, Warren 1984, then Stamens, they have discussed snowpack as a layer of dispersed spherical snow grains. So they modeled the snowpack based on this dispersed spherical by considering the snow grain as a spherical snow grains, and for that they have used the mu theory for the estimation of these scattering properties. And but in case of snow on ground, these are not the not uniform, these are not the spherical, these are the irregularly shaped non-uniform snow grains, and these optical property of snow are controlled by the size and the shape of the particles. So size, you have seen, the grain size was increasing, the reflectance was decreasing in NIRM. So that also depends on the shape of the particles. And then this Kokonowski and Jiggy, they have developed one theory, that is the asymptotic radiative transfer theory, that is called ART theory. And this theory was initially for the cloud, where in the cloud again there are the small ice particles, and similarly in the snowpack, snowpack is also made up of ice particle, and the same theory they have applied, and they have got very good estimation for the albedo and grain size. So I'll be talking on the application of this ART theory for the snow retrieval. So this is the equation given by Kokonowski and Jiggy 2004. So where this R the reflectance, and R0 is the reflectance once there is the no absorption in the snow, and RS is the spherical albedo, and F is a the function of mu 0 and phi. This is all solar and viewing zenith angle information. So this mu is cosine of solar zenith viewing zenith angle, and this mu 0 for cosine of solar zenith angle. This phi is the relative azimuth angle, and this RS spherical albedo depends on this parameter, that is S, is called similarity parameter, and this similarity parameters depends on this beta, the absorption, the snow, and this G, the asymmetry parameter, and mu 0 is where the single scattering albedo. So and this F also depends on here the phase function, and this they have given the Kokan SK and Jigi, they have given this the approximate solution of this this phase function by this equation, and from their model, this ART model, they were able to model this snow, this spherical albedo similar to that you can see here from theory, and it was close to the experiment result, except here in this region where this theory actually fails. There's a lot of deviation from the theory and experiment results. So with this ART theory, you can find that you can model the snow very well in this region. So from this equation, once you have the reflectance that you are getting measuring either from the spectrodiometer or through your satellite sensor, that's the major one. R0, in case of there is no absorption in the snow, that R0 was estimated using this equation here given by this one, and they have calculated these ABC coefficient over there. So these are the simple equations, analytical equations, and one can get finally this spherical albedo from a single measurement, reflectance measurement. And once you have this spherical albedo, you can also estimate this plane albedo. So that is again from the single measurement, reflectance measurement. Now coming to this snow grain size. So snow grain size, whatever we measure on the ground, mainly that is called equivalent grain size, and in that case we measure the maximum dia of the snow grains, or somebody do this maximum minimum dimensions of the crystals, and or the width of the branches, like that. So that is called the equivalent grain size. That is physically we measure using these crystal gauge and micromite. But using the optical sensor, we define this effective optical grain size by the ratio of this average volume of the snow grains by the average projection area. That's the average surface area. You can say volume to surface area. So from volume to surface area, one that is the definition of effective optical grain size. So this the snow reflectance function is governed mostly by the value of PPA, that is PPA is probability of photon absorption. So the retrieved effective radius has a clear physical sense over there, that because of this probability of photon, because of the absorption, you are retrieving here the effective grain size. So that absorption can be defined by this equation, this beta equal to C absorption by C extinction. So this absorption again you can calculate. This is a constant over here, safe constant that has been taken here. This alpha, which is the absorption coefficient defined by chi by lambda, and this extinction cross section can this is the proportion of geometrical cross section of the particle. So the I mean that this beta, the absorption, one can estimate by calculating all these C absorption and C extinction, and finally one can estimate the snow this effective grain size. So the another application is this specific surface area, and this is the same again, surface to volume ratio, the inversion of that. So once you have on the ground this surface area and you know the density of ice, you can estimate the effective grain size. So there are the methods given by Lagrange in 2002. There's some methane absorption techniques are there, micro tomography, near photography, near infrared photography, stereology. All these methods, from these methods one can estimate the SSA. So SSA value range typically from 2 meter square per kilogram for the melt freeze layer to 156 meter square per kilogram for the fresh dendrite snow. So we have done this exercise for the snow grain size estimation and the albedo using the same theory, ART theory, and here I am just showing the case study for that. This here we have got few the this Hyperion scene of our lower Himalaya, that's called, or middle Himalaya, or this upper Himalaya, and the Hyperion sensor which is on board on EO1 satellite and working since 2000, so having 30 meter spatial resolution and spectral resolution meter around 10 nanometer. So these are those different scenes of different ranges, and we have estimated the snow grain size for these regions. This atmospheric correction, this has been done using the flash module in the NB, and there are different standard atmospheric model and standard aerosol models. So we have tried all these models, and finally what we have found that since we have this hyperspectral data, so from that we can estimate the water absorption feature. Thus we can retrieve this water vapor. So we have found that this 1135 nanometer, this wavelength, this water absorption feature, this atmospheric model along with this 2-band KT, it was working very fine for our lower Himalaya as well as for our middle Himalaya, and this can be observed by these plots, that is plotted for these different combinations for lower and middle Himalaya. Here we have increased this NDSI threshold value from 0.4 to 0.6, and the refractance condition that so more than 0.6 in the green band, and again the incidence angle should be less than 75 degree. Based on this criteria, we have selected few channels, only the 5 channels we have selected for further processing, because hyperspectral data, again there is the problem for the huge voluminous data to process the data. So we have selected only those the bands from which we can get these grain size. So, and by applying this again ART model, we have estimated the snow grain size. But in Himalaya there is the different slopes aspects over there, so terrain corrections, this topography correction is very much essential to estimate the snow characteristic, and for that we have applied here the cosine corrections, and because this is one of the simplest model, we know we have also applied the other model, that's a Minute or the C models but we have found that the similar results were there. So this cosine in that case was a very fast model, and one can make it the operational. So for the topographic correction, the DM has been used of the 30 meter, and different local incidence angle images over there. Then there is the algorithm that we have used, that's a two-channel method. So in two-channel method, again this is the ART model, and in this ART model, uh, uh, here we have uh, considered uh, two equations for the two unknown. One is for the snow grain size, and another is for the suit concentration. So for two unknown you require two equations. So basically we wanted to to uh, to estimate the snow grain size, and where there should be no effect of any contamination in the NIR region. And for that we have used these equations. This is for the visible channel, the absorption in the visible due to soot, you can say, and this is the equation reflectance in the NIR region, where the absorption be due to the snow grain size, that's the ice, as well as if there is any effect of soot. So then with solving these equations, we finally have these equations to retrieve the effective grain size, and this model can take care of the pollution in if there is any effect of the pollution in the NIR region from where you are estimating the snow grain size. So these are the, the snow grain size map generated using 1240 nanometer and 1050 nanometer. So with these two wavelength region, you can see the mean grain size of the area, and these grain size are also very representative from our field stations, and from our field stations these mean grain size were very close to to this whole scene grain size. And here we have found there is the difference in the snow grain size using different channels, and this could be the probably due to, like, the less wavelength this penetrate more, and in the lower in the snowpack there may be the larger grain size. So there this type of the validation is required, where the vertical grain size variation one we have to measure at the time of the satellite pass and all. So unfortunately the ground data at the time of the satellite pass we don't have and this also give you from this grain size using multi channels, like this 1050 or 1240 nanometers, that it can give the idea about this vertical homogeneity in the snowpack. So like this is again for the middle Himalaya, and here again you will see this vertical homogeneity is is 1.18, or in this case 1.29. so if it is very close to 1, that is more homogeneous snowpack. And in this here middle Himalaya we have found the grain size is smaller than in compared to our this lower Himalaya. The reason is simple: in the lower Himalaya the temperature conditions were very high, and because of that the metamorphism uh, that proceed very fast in this lower Himalaya region in comparative to upper Himalaya. So that we have also observed from our field observatory locations, like here in the lower Himalaya, in this center we have one observatory here, where we record all the snow meteorological parameters, and similarly in this place we have the one observatory for the middle, which represent this middle Himalaya. And from that observatory data we have found, yes, the temperature range, if you see the snow surface temperature in the lower Himalaya range was in the range of -1, -2 on that particular day, 5th March 2010. However, in the middle Himalaya range, the temperature was very low, -21 in the morning time, in the evening it was -7. So that's why, and this snowfall was just the day 1 snow. Before that, the snowfall, the satellite date of pass of 5th March. So before that, the snowfall was taking place, and this was, you can say, the day 1 snow just after the snowfall. Even then, because of high temperature in the lower Himalaya, the grain size are higher uh, in this lower Himalaya in compared to your middle Himalaya. So again, using this spectroradiometer data, this is here we are, unfortunately, for the same day we don't have the field experiment spectroradiometer data, but we have the data of different dates of 2005 and of the same lower Himalayan range, and there we have found that the conditions was almost similar for in case of the lower Himalaya, where the surface temperature around -2. So that time it resembled very well with these grain size 312 or 265. So that you can see here also 308 and 239. So this type of validation is also very important once you retrieve the snow grain size. We have also taken this the grain size profile along the road, and you can see lot of variation in the lower Himalaya, where the grain size is varying right from the 200 to 700 or 800 microns. However, in the middle Himalaya, there is quite stable, and these are very close to 150 to 200 micron grain size in case of middle Himalaya. Then spherical albedo was also estimated, and these are the using the theory of ART, and you will find that in NIR region it resembled very well this theoretical model and the observed one, but in the visible region, yes, there is problem. So because since the ART model, whatever the equation has been given, that can model for the pure snow considering in the visible region, but here because of some pollution in the snow, that reflectance is the retrieved albedo, spherical albedo, is slightly lower than the theoretical model. Then this is the spherical albedo for the glacier area, and you can see the spherical albedo using 500 nanometer. This is for 1050 nanometer, the red one, and then blue lines, these are for 1240 nanometer. So you can see in the visible these are almost same for both the glaciers. This is one glacier G1, this long line, and this short line is for glacier G2. So the spherical albedo, however, is similar in this 500 nanometer range, but there is significant difference in this NIR region, and here we can say the application of for the glacier, like from this you can find out that there may be the this grain size will be very less, very large in case of the glacier number 2. So the silent feature of this study was the grain size was retrieved using this NIR channels 1050 and 1240 nanometer, along with this visible channel, and which can accommodate the absorption due to suit in NIR edges. And then the average retrieved grain size using 1050 nanometer were found larger than retrieved using 1240 nanometer, and which may be due to increased grain size with the snow depth. And but for that one has this in situ grain size the data. Both the NIR wavelength bands can work well for flat or gradual slope area, but from this study we have found that this wavelength 1240 nanometer is more suitable for the area having the steep slopes, because for this 1050 we are finding these with this wavelength some of the slopes were very saturating, where the reflectance was very close to 1, and then it was the grain size was not coming correctly. So here you can say 1240 is more stable in case of more suitable in case of the steep slopes. No spectral albedo product is presently available on the basis for on daily basis for Himalayan snow, but with this present technique you can retrieve the daily spectral albedo of products. The another application here I'll be talking on this grain size using this hyperspectral mapping method, that is SAM, spectral angle mapper, and the another is the identification of vegetation mix or the soil mix or the patchy snow cover areas. So again, for that, with the Hyperion data we have selected different parts in the lower Himalaya where there is fresh snow in the vegetation area, number one. In this area we have the snow in form of patches or contamination, so that we have tried to estimate. For that we have selected this scene, and then for the grain size, that is upper Himalaya, that we have already seen. So this is in this SAM method we have collected the end members using Hyperion image, and these are the mean of those end members you can see here, and these end members were collected with the help of this spectral library we have generated from our field conducted experiment. So based on that we have generated this library and estimated the grain size using SAM method. So this is the SAM classified map. This is the another method that I have discussed, the grain index method, and the third method for the grain size is ART theory method. So all these three methods, whatever I have discussed, we have made the comparison of these retrieved grain size. So where this SAM or this grain type, they are more towards, you can say, the qualitative type of grain size, is a fine, medium or the coarse range snow grains. But from this ART theory you are able to estimate more quantitative grain size estimation. So this qualitative also is required in many applications, like in the snow avalanches. There you are not going for the very fine retrieval, because we are not going to retrieve the albedo from the grain size. So in that case, if you only want to know this is the fine grain snow grain class or the medium snow grain class or the coarse snow grain class, in that case this SAM method is this grain index method, they are also equally very good. Secondly, we have compared this SAM classified map and grain size map, and this comparison, from that we have found there's a very good correlation between these different classes. Among these different classes, that's for the fine, this for the medium, so almost same area is coming, and this is for unclassified areas was common in both the classified maps. And by this matrix comparison, we have found this overall matching was also very good, around 80%, using the grain size retrieved using the SAM method and the grain index method. And that we have also compared again with this snow meteorological data of the another application is snow mix vegetation. So using Hyperion scene, we have again using this PPI methods, we have PPI scattered 3D scatter plots. We have collected the spectra for this the medium vegetation mix snow or this low vegetation mix snow, like that, and that we have also compared with our field collected these conducted experiment and generated these this is and applied the same methods, and where in this particular area you can see that this green is where the vegetation proportion is very high uh, with the snow, and the red where there's a low proportion, less than 50%, you can say, uh, the snow mix, the vegetation mix snow. And this we have validated with the help of the high resolution data, that here you can see the density of the vegetation is also very high in this area where you are getting this high vegetation proportion mixed with snow, and in this area we are getting here this red, this is the low vegetation proportion areas, and this is the selection of 3D end members using 3D scatter plot for the different classes, how it was collected, uh, and here this is the image spectra of contaminated and patchy snow. So this is for the light contaminated snow, this is for the heavy contaminated, and this is for the patchy contaminated. This was collected with the help of our the spectral library uh, with this, and these are this is the spectra collected for the different the contamination level, and with that again we have tried to identify the contaminated snow versus the patchy snow using this Hyperion scene. So you can see here uh, again that we have tried to correlate with our high resolution satellite images, and this is the area, this is the point, you can see the yellow in all the blocks where this the green is high contaminated or patchy snow. So we have got this green color on this edges over here, edges, on these edges the patchy snow cover, and along this road this is coming this the green high contaminated, and in the rest of the area we have found this the red, that's a low contaminated snow. So in this way we have tried to correlate this the contaminated and the patchy snow, because it's a very difficult, otherwise we should have ideally at the same time the ground validation through aircraft or through some sensors where or some ground sample should be there for the validation, but unfortunately all this type of validation was not there. So we have tried here with the help of high resolution images. So again the silent feature of this study was the same method was found as alternate method to retrieve snow grain size for the application where quantitative grain size are not required, so the qualitative is more. The same method was found useful to identify different level of vegetation soil mixing in snow. Since presently there is presently no method is available to quantify exact such mixing in rugged mountainous terrain to many because of the many challenges. Then the advantages of same type classification uses maximum bands of the hyperspectral imaging data and can provide many snow cover characteristics simultaneously with removing the noisy bands. On the other hand, identified suitable bands from hyperspectral data technique is important and useful for a particular parameter and application. The spectra of major ambient object, that's vegetation, ground cover, that all one has to be to collect the signature of all those type of vegetation which are there in the field. That's the select the end members for the selection of end members by the airborne hyperspectral imaging. This with high spatial resolution can be much useful in investigation of the snow. So the outlook of this study is the snow grain size, whatever we were estimating, that's a parameterization of snow grain size using field and lab based experiment is required, because whatever the grain size we are retrieving from the optical sensor, that is effective grain size, and whatever we measure on the ground, that is equivalent grain size, that we are measuring from our uh, uh, the graphs, crystal graphs. So this field validation using SSA or NIA technique, that is a must for our for the comparison of the snow grain size. Secondly, uh, from the spectral albedo data, we can develop the model for integrated albedo, and which is having lot of application in net radiation balance. Then for the quantitative estimation of the contaminants, so this instrumentation is required, the modeling is required to measure the exact quantity, that is the concentration, so either soot concentration or black carbon or the soil concentration in the snow cover. So this is still there's lot of work has to be done in this area. Then a good spectral average of different type of snow uh, with all ancillary data is required, and of course for the monitoring of response of this climate change on snow and glaciers, this is very important aspect, and where the changes in the glacier and the snow characteristic with the passage of the time or the temperature, that has to be required to monitor. Thanks.